When a user earns money for every second of video watched, the system must obey two entirely different laws of physics. On one side, you have the chaotic speed of streaming video. On the other, the unforgiving precision of a financial ledger. The media and ad tech side of the platform is the fast path. To load personalized content and run real-time bidding auctions, this environment requires high fan-out and eventual consistency, delivering responses in under 100 milliseconds. But the moment that watch time converts to user revenue, the data enters the strict path. This is the financial ledger domain. Here, speed takes a back seat to strict ACID database properties and immutable double-entry bookkeeping. A common mistake when designing this system is treating it like a standard CRUD application. This graphic shows a traditional microservices layout, separating the front end, creators, readers, and data management. But applying this simple decentralized model to Mo watch-to-wallet pipeline will break under load. To survive high-volume environments, you have to build on robust system design principles and cloud-native architecture. As this text outlines, understanding scalability mechanisms and network protocols is the only way to prevent catastrophic failures. If you try to increment user balances by running simple SQL update commands against a database, a single network timeout or dropped webhook will execute that retry command twice. At global scale, that means massive double crediting and drained corporate accounts. Architecting a platform like this requires bridging these two heterogeneous computing paradigms, the volatile edge and the immutable core. Global scale depends on the engineering of the boundaries between speed and consistency. We begin building at the user edge. The moment a client application opens, the system must instantly retrieve and rank personalized content. This discovery process relies on multimodal vector embeddings. By plotting users and videos as points in high-dimensional space, a hierarchical navigable small world index, or HNSW, maps the exact distance between them to generate highly relevant recommendations in real time. Once the user clicks, the video delivery mechanism takes over. The source file is transcoded into multiple bit rates and pushed through a multi-CDN architecture, streaming to the player in small chunks via HLS or Dash protocols. Concurrently, the edge triggers a programmatic ad request. Demand-side platforms assess the user's demographic data and submit their bids into a real-time auction that must clear in under 100 milliseconds. To process these rapid, highly variable requests without maintaining idle servers, we deploy serverless compute. As detailed in this reference, services like AWS Lambda abstract away the underlying infrastructure, executing code exclusively in response to incoming events. Because each invocation triggers an isolated runtime environment, the compute capacity scales automatically. If a live sports event causes a massive, sudden spike in traffic, the infrastructure expands instantly to match the exact workload. Within those milliseconds, the ad auction executes based on strict targeting parameters, matching zip codes and audience segments to ensure the highest-paying, most relevant advertisement is served. By isolating these high-velocity operations, the edge remains entirely decoupled from core financial records, preserving horizontal scalability to serve millions of users. Now we face the integration challenge. We need to capture every second of monetizable watch time generated at the edge without introducing synchronous locks that would pause or buffer the video player. The solution is an agent aggregator observability topology. A lightweight agent on the client quietly collects watch time metrics and forwards them to a centralized aggregator, ensuring the telemetry capture is entirely non-blocking. Those high-throughput telemetry events are then ingested into a partitioned, distributed message queue, like Apache Kafka, ordering the incoming data into a strict sequence. This introduces change data capture. CDC tracks every database modification as a discrete event, allowing us to replicate state across entirely decoupled systems. As this architecture pattern describes, relying on an event log allows the system to capture data changes without holding open connections to the main database. The log itself acts as the source of truth. This relies on what we call the state stream duality, the concept that a database's current state is the mathematical integral of all events in the log up to this specific moment. By using the log as our bridge, we capture volatile, high-speed telemetry from the edge and structure it into a durable, sequential audit trail ready for the financial ledger. With the data safely queued, we cross into the core ledger domain, where those Kafka events are consumed and converted into strict financial state. Because network timeouts and retries will inevitably happen, every transaction must be idempotent. This guarantees that if the exact same watch time event is processed twice, the system ignores the duplicate, preventing double crediting. Every movement of value is recorded in an immutable double-entry ledger. Money is never simply created or destroyed. Every credit to a user requires an equal and opposite debit from a specific funding source. This becomes complex when a single ad payment settles. That one payment must be instantly split into platform markup, payment processor fees, tax reserves, and the final creator payout. To manage this, we write the logic in NumScript, a domain-specific language designed for multi-party money movements. One incoming payment transaction cleanly splits into distinct paths for every fee, tax, and receivable. By defining explicit account paths for every destination, like isolating the merchant receivables from the platform markup, the system maintains total transparency over exactly where every fraction of a cent resides. Crucially, these multi-segment paths execute as atomic transactions. The entire batch of ledger entries either succeeds completely or it fails and reverts completely. This atomic constraint guarantees the platform's financial records never drift into partial or phantom states, keeping the internal balances flawlessly intact. However, our perfect internal ledger will inevitably disagree with external bank records. A card payment captured by Stripe tonight might not land in the bank's settlement file for 2 days, creating a timing asymmetry. To solve this, the ledger uses bitemporal tracking. By recording both when an event occurred and when the system recorded it, we can query balances at exact historical cutoff times, ignoring in-flight delays. At high volume, you cannot rely on manual reconciliation. Finding discrepancies requires a structured architecture running deterministic matching patterns. The most common is the many-to-one matching pattern. The reconciliation engine takes thousands of individual internal sales, sums them together, subtracts the mapped provider phase, and matches that total against a single net bank deposit. Any records that fail to match fall into an exception-based residual pattern, automatically routing the data break to an operational workflow for investigation. This automated control surface is the primary defense against audit risks. It ensures funds are properly safeguarded and segregated before regulators find a discrepancy. Reconciliation proves that the logic converting watch time into wallet value is actually functioning in the real world. Zooming out, we can see the completed high-level design. This diagram shows how raw application data flows through ETL processing layers and object storage, ultimately feeding the analytics layer. A single interaction starts at the high-velocity edge, streams through the Kafka buffer via change data capture, and finally settles into the atomic, immutable ledger. This structural mapping illustrates the core objectives of system design: evaluating business use cases, estimating throughput requirements, and designing robust solutions from first principles. The resulting architecture operates as a highly specialized machine, designed specifically to capture massive volumes of disorganized behavioral noise and distill it into high-fidelity financial truth. Integrating vector databases, real-time bidding, and atomic ledgers within a single pipeline creates immense potential for technical debt. Detailed system documentation provides the essential blueprint required to prevent a structural collapse. Engineering at this magnitude requires a transition from software maintenance to the intentional design of the rules that govern every data state. True technical leadership requires synthesizing the speed of streaming media, the latency demands of programmatic advertising, and the zero-tolerance rigor of fintech into a single cohesive architecture.